In this video, we're going to talk about how to evaluate other kinds of limits algebraically. So in this lesson, our little question is, how do we evaluate limits algebraically? If you remember, that's the same little question from the last lesson. In this lesson, we're just going to talk about some more strategies to evaluate limits. And as a reminder, by the end of Unit 1, you should be able to answer the following big question: how do we find the slope of a line using only one point? So let's go ahead and start with the warm-up. Again, if you're in class, you would be doing this on your own, but we'll discuss it really quick here. So what are the ranges of f of x is equal to sine of x and f of x is equal to cosine of x? Well, this is simply a factual recall here. So the range of both f of x is equal to sine of x and f of x is equal to cosine of x is the interval -1 to 1, including -1 and 1. So if you remember, sine and cosine are both waves. They're graphs, they're waves, and they go between the y values -1 and 1. Okay, so kind of like in the last lesson, we're going to look at some problems that can occur with limits, and that's going to motivate our different strategies for evaluating them. So let's begin with a problematic example. Find the limit of x squared times sine of 1 over x. The limit as x goes to 0. So first of all, let's think about why we can't use direct substitution. So suppose we do direct substitution. Then we get the limit as x goes to 0 of x squared sine of 1 over x is equal to 0 squared times sine of 1 over 0. Okay, so this right here is really bad because we can't divide by 0. So maybe you're thinking, well, 1 over x though, as x approaches 0, well that could be infinity. So, well, that's kind of confusing. Let me rephrase that. So 1 over 0 we could think of as a vertical asymptote. So that would be infinity. So maybe let's think about that. So if we then think about 0 squared times sine at infinity, so we don't really want to think of plugging infinity in as a number. So we're kind of thinking about this in terms of a limit at infinity. So the problem with that, though, is sine never settles on a value at large values of x. It only goes up and down between -1 and 1. So this doesn't really have an answer. And to better explain that, if we think about the graph of sine, it goes up and down like this. So at infinity, we don't know. So we call this oscillation when your y value goes up and down between two values and never settles on a single value. So we've seen before that limits don't exist when their one-sided limits aren't equal, but this is actually another way that limits don't exist, when they oscillate, which we just said was when they go back and forth between two y values and never settle. So we need a way to get around this problem because we still want to solve the limit. So to do this, we use what's called the squeeze theorem. So the idea of using a theorem to show an answer might be kind of new. So we're going to go through this a little slow. So the squeeze theorem says if we have some function g between two functions f of x and h of x when x is near a, and the limits of those two outside functions are equal, then we get that the limit of the middle thing is equal to those two values. So in English, let's translate all of that notation in English. So if we can find two functions, one greater than and one less than the function in our problem, each with the same limit, our problem limit is forced to have the same value as the bounding limits. So let's draw a quick picture. So what this is saying is if we have some function up here called f of x and some function down here called h of x, and let's say our limit is at a and a is right here, then if our function in our problem, g, goes between these two at this value of a, then all three of those must have the same limit. Okay, so it allows us to indirectly solve for the limit. And so this is kind of a new idea compared to a lot of the math that you've done up to this point. So let's see an example of how to do this. So we're going to go back to that problematic example, but this time we're going to be able to solve it. So find the limit as x approaches 0 of x squared times sine of 1 over x. So what we're going to do is we're going to start by bounding this function right here, this function in our problem. And the way we do this is through the range, because we know that limits are approximate y values. So we never want to think about them as exactly the y value. Sometimes they can be, but remember we're always thinking about it approaching some y value. So it makes sense to start with the range. Okay, so we know that sine is between -1 and 1. We said that in our warm-up. So the reasoning for this is the range of sine of x. And we know this already. Okay, so next we have sine of 1 over x is in between -1 and 1. And so this is because it's still the range of sine of x. So when we change that argument to 1 over x, that changes our x values, or it changes how smushed up x is, or sine of x is horizontally, but it does nothing to the y values. So we can stick with the same y values of 1 and -1 here. Okay, the next step, so remember we're trying to get to this function here, and so the next step to get it closer to that function is to multiply through our entire inequality by x squared. So that's what we're going to do. So when we multiply through by x squared, you notice that we get two functions, one on the left, one on the right, and that thing in the middle is looking really, really close to our problem now. So notice that these two look the same right here. Okay, so next we have our function now, but remember the problem was to take the limit. Well, easy peasy, we take the limit all the way across our inequality. So take the limit through the inequality. So now this thing in the middle is exactly our problem, and that's important. So what should happen now is these two limits need to be evaluated separately, and they should give us the same answer if the squeeze theorem is going to help us out. So this limit right here, pretty easy. We can do some direct substitution. And so if we plug in 0 for x, we get 0. And same thing over here. So we're going to do direct sub. And when we plug in 0 for x, we get 0 again. So what we did here is we just evaluated the limits on either side of the inequality. Okay, so the important thing here though is that both of those limits gave us the same answer. So we got 0 here, 0 here, and if some number, so what we're saying here is this limit that we wanted to find lies between 0 and 0. So maybe let's write that down. So our limit lies between 0 and 0. But what does that mean? Well, that just means that it is 0. So if something lies between a number and itself, well, there's nothing in between a number and itself except for that number. So, since the limits of the bounding functions are both 0, by the squeeze theorem, the limit in question is also 0. Okay, so take some time to look over that solution because, like I said again, this is a brand new concept that you really haven't seen before in most of the math that you've taken up to this point. So using a theorem to prove a solution to a problem is definitely a new concept. So take your time with that and make sure to ask if you have any questions. Okay, so next we're going to talk about another kind of limit solving strategy. So to motivate this, let's do a little recall. So what two kinds of asymptotes have we learned about and what type of limit corresponds to each? So for one, we had horizontal asymptotes. And those corresponded to limits at infinity. And second, we had vertical asymptotes. And those corresponded to infinite limits. Okay, so now let's think of some functions that actually have vertical asymptotes. So some that you should know, we have f of x is equal to 1 over x, and sometimes that's called a rational function. We also have f of x is equal to tangent of x, and so that's an example of a trig function. And another very common example that you should be aware of is the natural log of x, and that's a type of log function. Okay, so once again, those three examples show up all the time, so it's great to know that those three have vertical asymptotes, and it's great to know what those asymptotes are. Okay, so since infinity is not a number, so this is where our asymptote ideas are coming in with our limits. Infinity is not a number, so we can't use our previous methods for finding limits. So to evaluate infinite limits, we will have to use a verbal argument, which just means we're going to have to use words. So this means we're going to have to write complete sentences to explain why the limit is the answer that it is. Okay, so let's do an example. And again, this is a very new concept as well. You're probably not used to explaining your answers to math in words. So for example, let's find the limits. The limit as x approaches 3 from the right of 2x over x minus 3, and the limit as x approaches 3 from the left of 2x over x minus 3. So we'll start with from the right. So if x is close to 3 but larger than 3, so that's the meaning of this limit notation right here. We're choosing x values very, very close to 3 but larger than 3. Then the denominator is very close to 0 and positive. So if we take something like 3.1 and we subtract 3, we're going to get a really small number, so very close to 0, but that difference is going to be positive. Okay, the numerator is also positive. So if we think about plugging in 3.1 on the top, well, that's a positive number. So a positive number times 2, we're going to have a positive number. Okay, so now we want to think, on the top we're going to have a positive, and on the bottom we're going to have a positive. So when we divide these, the numerator by the denominator, we get a very big positive number since the denominator is so small. Therefore, the limit we want, so the limit as x approaches 3 from the right of 2x over x minus 3 is equal to infinity. Okay, so when you're writing a verbal argument, it's very important to take it step by step, sentence by sentence, and each sentence should follow from the other and make logical sense. So notice how we started with the denominator, we talked about the numerator, we combined the two, and then we said a conclusion at the end. Okay, that's very important. So now let's try the left-hand side. So if the right-hand side was a little confusing, because again, it's probably the first verbal argument you've seen in a while, or maybe ever. So we'll do another example with the left side, so that way you'll have two things to look at. So if x is close to 3, but smaller than 3, so again, we're coming from the left, so that's things just a little bit less than 3. Again, the denominator is close to 0 and negative. Okay, so if we imagine plugging in something like 2.9 and we subtract 3, well, that's going to give us a very small number again, like 0.1, but it's going to be negative because 2.9 is less than 3. Okay, however, the numerator is positive. So if we imagine plugging in 2.9 to the numerator, again, 2.9 is positive, so times 2 will also give us a positive number. Okay, so when we divide the numerator by the denominator, we get a very big negative number. So again, this is because the top is positive, the bottom is negative, so when we divide them, we have to get a negative number. And again, this is since that denominator is so small. Therefore, the limit we want, so the limit as x goes to 3 from the left of 2x over x minus 3 is equal to negative infinity. Okay, so those are two examples of verbal arguments. So the last type of limit we're going to talk about in this lesson are those limits at infinity. So this time, so we just talked about vertical asymptotes and how that gives us a verbal argument. Now we're going to talk about the limits at infinity, which are equate to horizontal asymptotes. So now let's think of some functions with horizontal asymptotes. So two that are really common that you should know are 1 over x. So that is that when the horizontal asymptote is 0. Also, we have d dx, and again, the horizontal asymptote equals, or actually, I shouldn't write it like that. I should say the horizontal asymptote is y equal to 0. And then a third one that's very common is inverse tangent. So we talked about that either in the last lesson or the lesson before that. So the horizontal asymptotes here are y is equal to plus or minus pi over 2. But the most important are these first two because that's how we're going to solve most of our limits at infinity. Okay, so to do limits at infinity, we need a couple of true facts. So number one, when we have 1 over x to a power, the limit as x approaches infinity or negative infinity is always 0. And that comes from that function 1 over x that we just talked about. Secondly, if we have the limit as x approaches positive or negative infinity of e to the minus or plus n times x, that's also going to be 0. So let me just make a little note of why these signs are the way they are. When you see signs, plus or minus signs that are opposites like that, what that means is as x approaches positive infinity, we have e to the negative x, and as x approaches negative infinity, we have e to the positive x. So the signs match up, but as opposites. Okay, so there's actually two facts embedded in there. Okay, so our goal with limits at infinity is to manipulate the expression so that we can take advantage of the true facts. So these tend to be difficult because they require a lot of algebra, kind of like the factoring ones in the last section. So you're going to need to know about roots, about foiling, multiplying through by algebraic expressions. So it takes a lot of algebra into account. So let's start with an example. So we're going to find the limit as x approaches infinity of the square root of 2x squared plus 1 over 3x minus 5. So first, we rewrite our problem, and that's our problem statement, and we've written that in our table. Okay, so next, so remember, my goal is to make 1 over x to some power appear as much as possible. Okay, so that's the main goal of all of this algebra. That's where we're trying to get to. So what we're going to do is we're going to multiply our function by 1 over x over 1 over x. So let me explain where this comes from. So 1 over x is the largest power of x in the denominator. And the reason we choose that is because that's going to give us the most 1 over x to some powers that we can possibly get. Okay, so we choose the largest power in the denominator. So let's summarize this step by saying we multiply denominator by what we call a well-chosen 1, and I believe we've talked about this before. So we say well-chosen 1 because we're multiplying by something over itself. So we choose this according to denominator's highest power of x. Okay, now our next step is to actually multiply that 1 over x through the square root and through the denominator. So we need to distribute. Now that can be kind of tricky when you're distributing into the square root, so let's summarize this step and then we'll talk about it. So we distribute 1 over x through the numerator and denominator. Okay, and so you might notice that under the square root, that 1 over x has turned into an x squared. Okay, so the reason that is because when you pull something under a square root, you want to think about it as undoing a square root. Okay, and the opposite of doing a square root is squaring something. So when we bring 1 over x under the square root, it becomes 1 over x squared. Okay, now we're just going to simplify all of those fractions. So we simplify each term in numerator and denominator. So notice here, when we do the division, x squared by x squared, we end up with just a 2. So we have that 2 right there. That 1 over x squared we can't divide anymore. The 3x over x, we get 3. And 5 over x, we can't do anything else with that. Okay, so this is our most simplified form. Now, notice we have these two terms that are a number divided by some power of x. Now, when we take the limit as x approaches infinity, those are always going to turn into zeros. Okay, so now we're taking the limit. So notice each of those in this next step turns into a 0. So here we say we use the true fact, limit as x approaches infinity of 1 over x to the n is equal to 0. Okay, so once those turn into zeros, from there we just do our regular arithmetic. So this last step, we just simplify / arithmetic to get final answer. Okay, so long algebraic process, but definitely doable. Okay, it's just going to take some practice. Let's try another example to try and solidify this idea. We're going to use a different true fact this time, though. So we're going to find the horizontal asymptotes of the function 1 minus e to the x over 1 plus 2e to the x. Okay, so let's write our goal over here, just so we know where we're trying to get. So we want to use the true fact, limit as x approaches plus or minus infinity is equal to e to the minus or plus n times x. I should have written equals there. So that limit is equal to 0. Okay, so let's start with the limit as x approaches infinity. So the limit as x approaches infinity of 1 minus e to the x over 1 plus 2e to the x, well, that's just our definition of a horizontal asymptote to the right. So we say definition of right horizontal asymptote. Okay, now this process is going to be pretty similar to the previous example, except we don't want to multiply by something over x, we want to multiply by something over e to the x. And it's kind of the same, so you just look for the highest power of e to the x in the denominator, and that's what you're going to multiply by over itself. So in this step, we're multiplying by well-chosen 1. Okay, so then the step after that is we actually want to distribute the 1 over e to the x. And when we do that, notice we have 1 over e to the x minus 1. So here I kind of skipped the step that we did in the last problem where we wrote out the fractions and then we simplified them. But if you need to see that, make sure you write that step out in between these two. And then in the denominator, we get 1 over e to the x plus 2. So that's our 1 over e to the x distributed. Now we can use the true fact. So here we're going to use true fact, limit as x approaches infinity of e to the minus x is equal to 0. So these 1 over e to the x's, that's the same thing as e to the minus x. So both of those are going to become a 0 in the next step. All right, and that's our true fact used. So then from there, we're just going to simplify / arithmetic. And we get -1/2 as our right horizontal asymptote. Okay, so in the next example, we're going to do the left horizontal asymptote. And so this one's a little bit different. So here, x is going to -infinity. So the true fact that we're going to want to use is the limit as x approaches -infinity of e to the positive x is equal to 0. Okay, so that's where we want to get. So The thing here, though, so I've kind of put this multiply by a well-chosen one here to trick you. So in this case, we actually don't need to do this because we already have e to the x, e to the positive x, in our problem. So what we can do is actually skip to the part where we use the true fact. Okay, so what's going to happen here is we actually can just skip to subbing in 0 for e to the x, and we get 1 over 1, which is just 1. Okay, so we can skip those 2 steps, and we get 1 as our answer. So, conclusion, remember our original problem was find the horizontal asymptotes, not the limit, so we need to make a little statement about that. So, the horizontal asymptotes of 1 minus e to the x over 1 plus 2 e to the x are y is equal to negative 1/2 and y is equal to 1. Okay, so the last thing you need to do in this lesson is just check your understanding, continue to answer that little question that we started in lesson 3. So again, I won't do that in the video, so that this is the end of lesson 4.